So, hello, am I audible?
Yes, sir.
So, hello everyone, I am Himanshu Mishra and I am the PhD scholar in the Department of Applied Mechanics, IIT Madras. And in this tutorial, we will be solving some question related to the radiation heat transfer. So, we will solve more couple of problems related to the radiation shield uh, and the some question that we have solved last week. We will extend uh, some of these more problems. So let's start with the last question we have left for the last week. So in this question we have given a long thin walled horizontal tube 100 mm in diameter is maintained at 128 degrees Celsius by the passage of steam through its interior. A radiation shield is installed around the tube, providing an air gap of 10 millimeter between the tube and the shield, and reaches a surface temperature of 35 degrees Celsius. The tube and shield are diffuse gray surface with emissivities of 0.8 and zero point 0.1 respectively. What is the radiant heat transfer from the tube per unit length? So we have a tube here and there is a shield. So diameter of tube is 100 mm and emissivity is 0.8, and diameter of a shield is 120 mm because it is given that there is an air gap of 10 mm around the tube, so it will be 120 mm for the shield. And this is tube. So temperature of tube is 120 degrees Celsius. Temperature of shield is 35 degrees Celsius, and there is a air gap between shield and tube, and we need to calculate the radiant heat transfer per unit length. So from resistance diagram, we can see that this is the radiation heat transfer from surface 1. So the resistance will be this, the air resistance will be this, and this is from the surface 2. So my heat transfer will be this will be my total heat transfer between surface 1 and 2. So my shape factor F12 will be 1 because all the radiation coming from surface 1 will eventually meet as surface 2, which means that F12 is 1 and F11 is 0, so we don't need this one. And my area A1 is pi d1 L and area it is pi d2 L. So my heat transfer per unit length will be this, and we just need to plug the values now. So this is my T1 Boltzmann constant. My temperature is given as 120 degrees Celsius. So I am converting into Kelvin. And my emissivity of tube is 0.8 and emissivity of shield is 0.1. This is my diameter of tube. And this is my emissivity of shield. So on calculating this, we will get heat transfer per unit length as 30.2 watt per meter. So here in this question, we have given a circular tube which is completely surrounded with a shield, and we have given the emissivity of both tube and shield, diameters and temperature, surface temperature, and we need to find the heat transfer. So we use the concept of resistance to define the expression for total heat transfer, and by inspection we just found that the shape factor will be 1. That means all the radiation coming from surface 1 will land it to the surface 2, and then we just plug the values in the heat transfer expression to just find the heat transfer per unit length. Any doubt in this question?
But actually, we are not taking that emissivity of outside surface of the shield. Are these emissivity for inside and outside surfaces for shield are independent?
Emissivity of sorry, I did not follow your question completely. Can you just repeat? Hello?
Emissivities, one will be inside, which is facing the pipe, and another will be outside, which will be facing the ambient air.
Yeah, so
So we are not taking into consideration the emissivity outside because
because we have not given it, we have no data emissivity of outside, so it is just the emissivity of tube and the inside emissivity of the shield, which we have given in the question. That's is sufficient to solve this.
okay.
Yeah. So let's move to the next one. So in this question, a flat bottomed hole 6 millimeter in diameter is bored to a depth of 24 mm in a diffuse gray material having an emissivity of 0.8 and a uniform temperature of 1000 Kelvin, and we need to determine the radiant power leaving the opening of the cavity, and the emissivity, effective emissivity of a cavity is defined as the ratio of radiant power leaving the cavity to the black body, and we need to calculate the effective emissivity of the cavity described above. So here in the question you have so this is our geometry. So we have a surface which is bored to, let's say, till L24 mm, and the diameter of a hole is 6 mm, and the emissivity of these inside surfaces is 0.8 and the temperature is 1000 Kelvin, and we need to find the heat transfer. So let's make an imaginary surface here, and let's say this is my surface 2, and remaining surfaces are 1. So from the again we can use just a resistance concept, and we can see there will be a heat transfer from surface 1 to surface 2. So this is from surface 1, this is the air resistance, and this is at surface 2. So my heat transfer will be same as in the previous question. So from inspection we can see that whatever the radiation, uh, so we cannot, in this question we cannot say the shape factor f12 equals to 1, because whatever the radiation coming from surface 1 can still fall on surface 1, or another way around as well. But we, from inspection we can say that whatever the radiation which comes from surface 2, all the radiation will definitely land to surface 1. So my F21 equals to 1, but my F12 is not equal to 1. So we can use the reciprocity theorem to calculate the F12. It is just A2 by A1. So my A2 is just pi d square by 4, and my A1 is pi d square by 4 plus pi dl. So this is my shape factor F12. So my D is 6 mm and my L is 24 mm. So I'm writing in the SI units. So On calculating this, just calculate. So my F12 will be roughly around 0.4, and then I just need to substitute in the heat transfer relation all the values. So my epsilon 1 is zero point 0.8, and my epsilon 2 will be 1 because there is no surface. The surface is imaginary. So my epsilon 2 will be 1. So my epsilon 2 will be 1. So this term will be vanished. So we have only this and this term. So my heat transfer will be so the temperature is 1000 Kelvin. And let me take the outside temperature as 293 Kelvin. So my emissivity of the surface is 0.8, and my area is 4.8 10 to the power minus 4 plus 2.8 10 to the power minus 5 plus 0 because this term will be 0. So on calculating this, we will get the heat transfer roughly equal to 1 watt. Now in the second part, we have given the definition of effective emissivity, which is the heat transfer that we have found divided by the black body heat transfer. So the effective emissivity will be Q by rho T1 A2. So it will be 1 by pi by 4, 6, 10 to the power minus 3 square. Temperature is 1000 Kelvin multiplied by 5.67 10 to the power minus 8. So then we can calculate here. So on calculation, we will get the effective emissivity around 0.9. So this question is very similar to the previous question. So in the question it was given that we have a surface and we drill the surface to form the hole, and then we need to find the radiation heat transfer from the inside the hole to the outside, and we have given the emissivity inside the hole, and then we use the resistance concept here to find the total heat transfer, and then to calculate the shear factor we use the reciprocity theorem that we have discussed in the previous weeks, and we found that the shear factor F12 is around zero point 0.4, and then we just substitute into the formula, heat transfer formula, to calculate the total radiation heat transfer. Then in the next part of the question, they have given the definition of the emissivity. They said that it is the ratio of the heat transfer to the black body radiation. So by using that definition, we calculate the effective emissivity of the for the given problem. So any doubt in this?
Sir, this surface one,
Yeah.
you have this surface one, is it a cylinder?
So yes, it is. And so basically, this is a hole with a diameter. This is a sphere. Any more doubts? So let's move to the next question.
Hello.
Hello. Yeah.
Yeah, sir. Actually, I am just want to clarify
Uh, yeah.
one thing from the previous question,
Yeah.
that you have taken the surface one as a whole, that base as well as the curved surface, whole as a one.
Yes. Yes.
But the base is having F11 base. If we are taking base is 1, then that will be F11 is 0. And then the curve for curved surface, that F11 will not be 0. So how we can club these two type of surfaces together, because they are having different characteristics. One is concave and one is plane.
Yeah. So F11 is not zero. We don't need F11 at all in this question. We just need to find the F12. That's it. And we know that the F21 is 1. So we can use the reciprocity theorem to convert F21 into F12, and F12 is the needed to solve this question. So F11 is not 0 and it is also not needed at all. So we don't need to bother about F11.
F, like if I take bottom as 1 and curved surface as 2 and the top surface whole as 3,
Yeah.
then 1 and 2 are having different nature. For 1, F11 will be 0, and for 2, F22 will not be 0. So we are clubbing 1 and 2. I think you might be understanding that if I am taking the bottom as 1, I am taking the curved surface as 2, and the hole which is at the top as 3. Like you have taken top as 2. I am taking it, this one is this, this is 3. So 1 and 2 for F11 is 0. F22 will not be 0. We can't club these two.
Yeah, F22 will not be 0 then.
Yeah, so we can't take 1 and 2 the same.
But why? See,
Because they are having different characteristics.
no, they are not having different characteristics. They are the same. They are made of the same material, and they have the same temperature, 1000. So this is at 1000 degree, sorry, 1000 Kelvin, and the bottom one is at 1000 Kelvin. Now the problem is, like, if you do in this way, there will be no heat transfer from 1 to 2 or 2 to 1 because they are at the same temperature. So basically you are doing 1000 Kelvin to the power 4 minus 1000 Kelvin to the power 4. So the heat transfer will be 0 here. The only thing is the shape that the resistance will be modified. It will have the extra resistance due to the surface 3 and due to the space between 3 and 2 and 3 and 1. So the resistance becomes much more complicated, and the heat transfer, there will be multiple uh, way of a heat transfer from surface 1 to 3, from 1 to 2. From 1 to 2 it will be 0, and then there will be only heat transfer from 1 to 3, and you need to accommodate the suitable resistance between 1 to 3 itself. So it is better to take the side and the bottom surface together because they are at the same temperature, and then calculate the resistance, and then calculate the heat transfer between the remaining surfaces, because it will simplify the problem, and we don't need to bother about multiple way of heat transfer, because then we have to consider different surfaces and heat transfer between the different surfaces at all. If the side surface is, let's say, at a different temperature, then the problem will become much more complicated, and we can divide the surface like this like this. We can use charts, or let's say some empirical correlation to find the different shape factors. We modify the total resistance between surface 1, 2 and 3. Then we find the different modes of heat transfer, like from surface 1 to 2, 1 to 3, and then we combine them to find the total heat transfer. It will become a huge complicated problem, but fortunately in the question it is given that all the surfaces are at same temperature, and these are the same material. Emissivity is same for all the surfaces also. So which means that we can easily take entire surface as a surface 1, and we can have an imaginary surface as a second surface, and we can just directly calculate the heat transfer between surface 1 and surface 2.
Okay, sir.
Yeah. So let's move to the next question. So in this question we have given a long V groove of a 10 mmD machined on a block that is maintained at again 1000 Kelvin, and if the groove surfaces are diffuse and gray with an emissivity of 0.6, determine the radiant flux leaving the groove to its surrounding. And so again it's a similar question. So we have a groove and we have a emissivity of the wall is 0.6. Let's say this is my surface 1, and again my imaginary surface is 2, and can assign some temperature to it, and normal air temperature which is around 293 Kelvin, and my temperature of surface is 1000 Kelvin, and the total length of a groove is 10 mm. Yeah, 10 mm. So by using the resistance concept, we can just formulate the resistance for every surfaces. And then my total heat transfer will be same as we discussed in the last two questions. Hmm. Now my emissivity at 2 will be 1 because it's just an open surface. So again this term will vanish, and we can just calculate f12 again. The f12 will not be equal to 1 because there is some radiation which will fall back to surface 1, but f2 1 will be 1. So again we will use the reciprocal theorem. One. So I can just directly write this term as f21 a2 or as a2 because my f21 is 1 from the reciprocal theorem. So this whole term will be just a2. That's it. And from trigonometry, this is my L. This is my L. Let's say this is my theta. We have given anything. Yeah, we have given this 40 degrees. So this is my 20. This is my 20. So this theta is 20. So this side is L10 theta, and this is my L by cos theta. So my A2 by A1 will be 2 L10 theta by L by cos theta, basically this and this. So it will be sin theta. So my heat transfer will be here, rho T14 to 4 1 by A2. And what I need to be radiant flux. So basically I need to find the radiation flux here. That means the radiation heat transfer which is crossing from surface 2. So my radiating flux will be, which is the radiation heat transfer from surface 2, will be by A2, which means T1 to the power 4, T2 to the power 4 will be 1 minus E1, A2 by A1 plus 1. So this will be my radiating flux here. I just divided by A2 at both sides. That's it. So my A2 by A1 is just sin theta. So my Q by A2 will be, I'm just putting the value in this expression. Thousand Kelvin, and the ambient temperature I considered as 293. and my emissivity is 0.6 multiplied by sine what is 20 degree plus 1. So on just calculating, I will get my heat flux as around 44 kilowatt per meter square. So the question was similar to the previous one. We have given the triangular groove and we asked to calculate the radiant flux leaving the groove to its surroundings. So basically we are asked to find the radiation heat transfer leaving the surface to the surrounding. So we use a resistance concept to formulate the total heat transfer, and from inspection we found that the uh, we found the shape factor f21, and then we use the reciprocity theorem to find the shape factor f12. Then emissivity 2 is 1, which means that this term will be vanished, and we modify the heat transfer formula to the radiant flux, which is basically heat transfer divided by an area or area A2. We just substitute the values and we found the heat transfer uh, flux, radiant heat flux for this problem. So any doubt?
No, sir.
Okay, then let's move to the next question. So a very long electrical conductor 10 mm in diameter is concentrate with cool cylindrical tube 50 mm in diameter whose surface is diffuse and gray with an emissivity of 0.9 and temperature of 27 degrees Celsius. The electrical conductor has a diffuse gray surface with an emissivity of 0.6 and is dissipating 6 watt per meter of length. Assuming the space between the two surfaces is evacuated, calculate the surface temperature of the conductor. So this is my cylindrical tube and this is my conductor, and we have given the temperature of cylindrical tube as 27 degrees Celsius and emissivity, let's say this is my surface 2 and this is my surface 1. So my emissivity is 0.9 and my emissivity of conductor is 0.6 and my temperature is not given. This is unknown quantity, but the radiating heat transfer between two surfaces is given per unit length, which is 6 watt per meter. So this is the radiation heat transfer between two surfaces, and we have given the conductor diameter, which is d1 10 millimeter, and tube diameter, which is 50 millimeter. So we can basically apply the same resistance concept here. Just to write down the total heat transfer equation. Now a heat transfer equation will be this is a general expression. Now in the last class, we simplify this expression for the two long cylinders. By simplification, I mean that here we know that f12 equals to 1. So when I put f12 equals to 1 and also this a1 by a2 equal to r1 by r2 or d1 by d2. So when we put these two condition here in this expression reduces to 1 by epsilon 1, 1 minus epsilon 2 by epsilon 2, r1 by r2. So this is our general heat transfer relation which we got from the resistance function, and this is for only two parallel cylinder which we got from these two basic fundamental concept which is given in the question, because it says a long cylinder, which means that my area A1 by A2 is directly proportional or just equal to R1 by R2, and my shape factor F12 will be 1, that which means all the radiation coming from 1 will go to surface 2. So by putting this and these 2 points into the general heat transfer expression, we will reduce our heat transfer relation for the two long parallel cylinder. For the spherical one, my area A1 by A2 will be equal to R1 square by R2 square. So here will be square term for the two parallel spherical case, and for the cylindrical case it will be just R1 by R2. So we just need to plug in the value. So we have given the heat transfer here, and we need to find the T1, because the T1 is unknown quantity and we have given T2 and all the emissivity, which means on simplification so this will be my expression for T1. So we just need to plug the values. So my T2 is 27 degrees Celsius. So I will be writing in Kelvin. My heat transfer per unit length was 6, and my emissivity is 0.6 for surface 1 and 0.9 for the outer surface. And my ratio of radius will be 1 by 5. So on just calculating this, I will get my T1 is around 342 Kelvin. So again we have given a two long parallel cylinders and we have given the heat transfer, and we need to just find the temperature. So from the resistance concept we define the general heat transfer equation. We then further simplify to the case for the two parallel cylinder, and then we have already given the heat transfer. We just need to find the temperature. So we adjust our expression to find the expression for the temperature T1, and then we just plug all the values to calculate the temperature T1. So any doubt?
Sir, this denominator you please explain again. the denominator you have written for Q dot.
Q dot non where?
This rate of heat transfer you have written, no, for two parallel cylinders.
Yeah. This. So basically, I'm just simplifying the expression here. A1. So this will be just my A1 because my F12 will be 1 and A2 2 by A2. So now what I'm doing, I'm just dividing in. So I can write this as 1 plus 1 minus A2 A1 by A2. Oh sorry, I miss A1 here. So basically I'm multiplying and dividing the this. I'm doing this. So I'm multiplying with A1 and I'm also dividing with A1. So I will get here A1. A1, A1 and here will be A1. So by doing this, I can write this expression like this. Now I can just further simplify. I just add plus 1 to this expression. So I will get 1 by epsilon 1 plus 1 minus epsilon 2 by A1 by A2. So this will be my modified resistance for the cylindrical case. So here it will be A1 and this I will get when I multiply and divide it by A1 to the heat transfer relation. So yeah, I missed A1 here. Is it fine? So basically I am writing
Yes, now it is okay, sir.
yeah, A1 here, A1 here and A1 here and also A1 here. So it will be A1 here and it will become, this will be actually A1 by A2. So then let's move to the next question. So liquid oxygen is stored in a thin walled spherical container of 0.8 m meter in diameter, which is enclosed within a second thin walled spherical container of 1.2 meter in diameter. The opaque diffusive gray container surfaces having an emissivity of 0.05 and are separated by an evacuated space. If the outer surface is at 280 Kelvin and the inner surface is at 95 Kelvin, what is the mass rate of oxygen lost due to evaporation? So we have given two parallel spherical surfaces. Let's say this is my outer surface and my diameter of outer surface is 0.2 meter. Temperature of outer surface is 280 Kelvin and the emissivity is 0.05. And for the inner one, my diameter of inner one is 0.8 meter. My temperature is 95 for the inner surface. My emissivity of inner surface is also 0.05. And you need to find the mass rate of oxygen lost due to evaporation, and we have given the latent heat of vaporization of oxygen, which means there will be a heat transfer due to evaporation also, or the boiling, evaporation here due to the evaporation, and which can be given as by this relation. So we already have given this latent heat and we need to calculate the mass rate, which is m dot, which is an unknown quantity. So from the energy balance, I can write that whatever the evaporation will happen, it will due to the radiation heat transfer. So my Q will be HFG, and it can be uh, equal to rho T1 to the power 4 minus T to the power 4, and resistance. This resistance is similar to the previous one. So my resistance can will be this. So this is my general heat transfer relation. Now again I can multiply and divide it by A1 here. So I will get rho A1 and I will get here. You can just cut both A1 here. Here it will be just 1, and here it will be A1 by A2. So for the spherical surface, my A1 by A2 will be equal to R1 by R2 square. So for cylinder case, it was just R1 by R2. For the spherical surface, it will be R1 by R2 square. So the expression becomes 1 by epsilon 1 minus epsilon by epsilon 2 R1 by R2 square, and my mass rate will be this. So we just need to plug in the values. So this is my area A1. My T1 is 95 and T2 is 280. And HFG was 2.13 10 to the power 5 joule per kg. Result is 0.05. And my ratio of radius or diameter is 0.8 by 1. So on just calculating this, I will get the mass rate equal to, I'm writing in the modulus plus, I don't need this sign and all, 10 to the power minus 4 kg per second. So this is my magnitude of the mass rate. So in this question we have given two parallel spherical surfaces, and it is said that there will be an evaporation and we need to find the mass rate of the evaporation. So the source of energy is the radiation heat transfer. There will be a radiation heat transfer due to which the one surface will get heat up, and there will be a evaporation heat transfer also occurs. So it will be my output heat transfer. So from energy balance I can just write my radiation heat transfer equal to the evaporation heat transfer. So my evaporation heat transfer will be just m dot hfg, and we have already given the latent heat here, and we just equate this relation to my radiation heat transfer uh, expression. So from resistance function we calculate, we derive our general radiation heat transfer expression, and then we modify to the parallel spherical surfaces. And from this relation we calculate the mass rate. So any doubt?
No, sir.
Okay. So let's move to the next one. So a thin aluminum sheet with epsilon emissivity 0.15 on both sides is placed between two large parallel plates which are maintained at uniform temperature 900 Kelvin and 650 Kelvin with emissivity 0.5 and 0.8. Determine the net heat transfer with and without no shield. So let's say we have two parallel plates and there is a radiation shield between them. So emissivity here, let's say this is my 3, 1, 2. So emissivity is 0.15. So emissivity at both sides like 0.15. So 3.1 is this part and 3.2 is this part. This is my emissivity for 1, which is 0.5, and emissivity at 2 is 0.8. Surface temperature at 1 is 900 Kelvin and surface temperature at 2 650 Kelvin, and we need to find the heat transfer without this shield as well as with this shield. So my resistance will be so it will be 1 minus A1 F1 2 1 minus A 3 1 A3, and it is 3 2 it will be A3 F3 2, and this will be 1 minus epsilon 2 A2. So this will be my total resistance with shield. So this part is the radiation heat transfer from surface 1 to 3, and this part is the radiation heat transfer from between the surface 3 and 2. So
Sir, shouldn't this second term be F13?
second term at
Like from left, if we are moving, then 1 by A1 F12 you have written, it should be 1 over A1 F13.
oh, sorry. Yeah. Yes. So everything is correct. Hmm. So my heat transfer time between plate 1 to plate 2 will be, so basically these two terms are same because my emissivity is same here, is 0.1. I'm just multiplying with 2. So we can further simplify this expression according to our point. So here F13 will be 1, F32 will be 1, and the surface area will be all equal to each other. So I'm writing 3 1 equal to E3A. Or so I can further simplify it to this and this. Well, so this first part and this last part will become 1 by epsilon 1 plus 1 by epsilon 2. And this part is, so this is my modified relation. Now I just need to plug the values. So this is my heat transfer with shear. So heat transfer with shear is my emissivity or given is epsilon 1 is 0.5 and epsilon is 0.8. And epsilon 3 is 0.15. So on calculating this, I will get with shear the temperature is 1857 watt per meter square. This is my temperature with shield. Without shield, the resistance will be simplified very much. So it will be just we used in the previous questions. So the radiation it transfers just between surface 1 and surface 2. So this is without shield. So this is without shield. So again we can just simplify the problem. A1 equals to A2 and F12 equals to 1. So after putting this simplification into the resistance functions here, I can just directly write the expression like this. So this is without shield. So I'm just putting the values. So I'm calculating, I will get with shield, my radiation heat transfer is around 12,035 watt per meter square. So when I take the average with shield and without shield, sorry, not average, the ratio is roughly around 1 by 6. This is my ratio between the heat transfer with shield and without shield. So in this question we have given a problem of two parallel plates and there is a shield between them and we have given the emissivity of all the surfaces and we formulate the resistance for all three surfaces to find the total heat transfer, and we have done the same thing without shield also, and without shield the resistance concept become much easier, and this is the same resistance we are using since many questions. And then we calculate without heat transfer without shield as well, and then we calculate ratio in the end. So any doubt in this problem?
But the resistance network you have written, the third term should also be E13 and not E31. It should be E13, isn't it?
Where?
The resistance network you have written here, the
Yeah.
second term. The resistance network you have.
Or which shield, right?
That first one is 1 minus epsilon 1 over epsilon A1, then second is 1 over A1 F13. The third one, 1 minus epsilon 3 1 you have written. I think it should be epsilon 1 3.
Uh, no, so this is actually from surface 3 to 1, not 1. So this property is emitting from surface 3 and this is emitting from surface 1. So, I mean, it is for from surface 3 to 1. So, I think the notation is correct because I mean, it is just a matter of rotation. Like even if I write this, it should be coming out from surface 3 because this is the so this is the radiation from emit from the surface 1. Then this is the space between 1 and 3, and this is from 3. This is should be from 3. So this emissivity should come from surface 3 towards 1. This is coming from 3 towards 2. So it is again coming from 3. This is the space between 3 and 2, and this radiation should be coming from 2. So I guess it is just a matter of notation, that's it. Anyway, it should come from, so this part should come from 3 towards 1 and this part should come from 3 towards 2. And this.
Okay, okay, sir.
So in this question, two large parallel plates are maintained at uniform temperatures, T1 1000 Kelvin and T2 800 Kelvin, and we have given the emissivity, which is 0.2. Now to reduce heat transfer by 1/5 by placing the thin aluminium sheet of emissivity 0.1 both sides, calculate the number of sheet required. So we have given two surfaces here. This surface is, let's say, 1 and this is 2. T1 is equal to 1000 Kelvin. Here T2 equal to 800 Kelvin. Emissivity here is 0.2 and here is also 0.2. Yeah. And it is given in the question that we need to place the radiation shield to reduce the heat transfer by 1/5. So we need to calculate how much number of radiation we require to reduce the heat transfer by 1/5. So this is heat transfer without shield and this is heat transfer with shield. So from the resistance function that we have using since so many questions, I can just directly write the heat transfer for without shield. Is epsilon 1 2 minus 1, which is exactly the same relation that we have discussed in the previous question and since many questions here. And this is for the without shield case. So when we plug the values, this is, now we just need to find the values here. So my heat transfer without shield will be 3720 watt per meter square. So with shield, my total reduction should be 1/5 to whatever we have found. Sorry. So whatever the heat transfer will be we have found here, it should be reduced by 1/5. And from the above expression here, we derive a general expression for the three parallel plates here. So we can just write this part as it is. So for unknown number of shields, the expression will be given as so this emissivity is for the first plate and the last plate, and between the first plate and the last plate there can be an n number of radiation shield. So for such cases the expression can be given as, this is my n number of shield multiplied by 3 1 3 2 minus 1. Now my emissivity 3 and 3 2 is equal, let's say E3, which is 0.15, and I need to calculate the total number of shield here. So I already know this QS, or which is QW by 5, which we have found without which is heat transfer without shield divided by 5. So it will be QW by 5. Like 2 by epsilon 3 minus 1. So basically I'm just multiplying n here, that's it. So this is the expression for unknown number of shield, which is given by n. So my QW is 372055. This is my Boltzmann constant. I have already given the temperature and emissivity, which is 0.2. And n is unknown. Equals to 5.67 and minus 8. So on solving this expression for n, we will get n as 2.92. So the n should be not a integer with some decimal number. So we will approximate it n as 3. So we require 3 radiation shield to reduce the heat transfer by 1/5. So here in this question we have given a two parallel plate. We have given the temperature and emissivity of two parallel plates, and then we ask to place the number of shield between them such that the heat transfer reduced by 1/5. So we use this relation, this expression in case we don't know how many radiation shield we need to fix. You just can remember this this expression. So this expression is only valid for the unknown number of shield for parallel plates. So only for parallel plates, and if the number of shield is unknown, we can use this expression and we just plug all the values to calculate the capital N. So any doubts in this question?
No, sir.
Okay, so let's move to the next question. So this PDF is actually from the previous semester of the heat transfer course. So I will be solving few questions from this PDF. I will upload this PDF in the drive. So remaining questions we already solved. So this question we solved already, and this question is also we solved in the previous class. So in this question, the two concentric spheres of diameter d, I think no, we have not solved this. Yeah, D1 0.8 meter and D2 1.2 meter are separated by air space and are surround surface temperature of T1 400 Kelvin and T2 300 Kelvin. If the surfaces are black, what is the net rate of radiation heat exchange between the spheres? This is the first part. The second part is what is the net rate of radiation heat exchanges between the gray, diffuse and gray surface. We have given the emissivity 0.5 and 0.05. In the next part, the diameter changes to 20 meter, and then emissivity is also changes. Emissivity is same, and then we need to find the heat transfer again. So we have a two spherical surface. So we already solved the similar question. So let's say this is my surface 1 and this is my surface 2. For surface 1, the diameter is 0.8 meter, temperature is 400 Kelvin, and emissivity is point. Oh, we are solving for the first part. In the first part, the surfaces are black. So for now, the emissivity is 1. And for surface 2, the diameter is 1.2 meter for now, and temperature is 300 Kelvin. So for the black body, black surfaces, so both surfaces are black. So heat transfer will be just given by Stephen Boltzmann law. So my F12 will be 1 here. So we can check from the summation rule. So this is 0. So F12 should be 1. This is my surface area of sphere 1. For the black body, my heat transfer will be just solving this will be 1995 watt. So this is my heat transfer for the when the both surfaces are black. Now if both surfaces are gray and we have given the emissivity of both surfaces epsilon 1 and epsilon 2, you can just use the resistance concept we are already using. So my heat transfer for the gray surface will be. So I'm just directly writing the modified expression because we have already solved a lot of problems. Especially we have also solved this problem. For the spherical case, we saw that the area A1 by A2 equal to R1 by R2 square. So on gray surface, this is my surface 1 emissivity. This is surface 2. My R1 by R2 is 0.4 by 0.6 square. So on solving this, we will get the gray surface heat transfer around 191 watt. Which is quite obvious. It should be less than the heat transfer to the black body. Now in the third question, the diameter D2 increased to 20 meter. So the resistance are same. It is just here the diameter increased to 20 meter. So instead of 0.6, we can just write 0.4 by 10 whole square. And then we have to find the same heat transfer with the modified diameter. So that you can do, you just then calculate the modified heat transfer, which is, let's say, Q dash, with the same temperature of both surface. Emissivity is same. And only there is a change in diameter, which is 10 now. Hello, Naren, can you switch your mic? Yeah. So now this is my modified heat transfer with change in diameter, let's say, which is D2 dash. So just try to calculate this with modification in diameter. So this is the C part. So in this question we have given the two parallel spherical surface, and in the first part we need to find the heat transfer considering the both surfaces are black, and we use the Stephen Boltzmann law to find the heat transfer. Next surface, for the next part, they said that the surfaces are gray, so we have given the emissivity of both the surfaces. So we use the standard procedure to by the track down all the resistance, and then uh, develop the expression for the heat transfer based on the resistance function, and we found the heat transfer with a gray surface. In the last part C, the diameter increases to 20 meter, so we just need to substitute the modified diameter again in the same expression to find the modified heat transfer due to change in diameter. X. So any question?
Sir, in this, for the black body, you have written Q is equal to A1 F1 to sigma T1 raised to power 4 minus T2 raised to power 4. And for the gray surface, it is sigma T1 raised to power 4 minus T2 raised to power 4, and in the denominator, emissivity and the radius system is there. So will this Q be that Q for the black body and Q for the gray will have the same units? No,
Yeah.
because there is area in the numerator and here there is no area.
No, you will get. So A2. So now, so this is the heat transfer for the gray surface. That it's a general heat transfer for gray surface that we are using in many questions. So try to put epsilon 1 and epsilon 2, 1 here, and when you do that, you will get this rho T1 by T1 to the power 4, T to the power 4. So this term will be vanished, this term will be vanished, and you will get only this F1 2. So you will actually get back the heat transfer for the black body. So this is the heat transfer for the black body. So the units are same. Here we just modify our expression for the two parallel spherical case. We multiply here A1. So here we multiply and divide it by A1. So by doing that, we will get this expression. That we already done this with the cylinder.
In gray body, that in numerator, A should be there.
Yeah. A1 is there.
No. Yeah, there, what the expression you have written at the bottom.
Here we multiply and divide it by 8. So this again will become.
Yeah, so that in numerator A should be there, na?
Yeah. I again forgot.
Yeah.
Yeah.
This is the point I want to make, clarify.
Yeah.
Okay.
I am forgetting even here. So yeah, this is the problem. So let's move to the last one here. So again, I think we solved this problem already in this class. So I will just again resolve it with different numbers. So we have given a thin aluminium sheet with emissivity of zero point 0.1 on both sides is placed between two very large parallel plates. The temperatures are given and the emissivity of parallel plates are also given, and we need to determine the net radiation heat transfer. So basically there are two plates and there is one aluminium sheet. So the temperature here is, let's say, this is 1, 2, this is 3, and this is 800 Kelvin, and this is 500 Kelvin. The emissivity is 0.2 here, and here it is 0.7, and its shield it is 0.1 at both sides. So we already know the resistance function because we derived the resistance function with shield. So and then we simplify the relation for the same case. So I'm just gathering data from the last question. So I can just directly can write down the heat transfer relation, which is um, 1 by epsilon 1, 1 by epsilon 2, and this is my shield. So this is the expression we already derived, and we need to find the net rate of radiation heat transfer per unit surface area, Q by A. We just need to plug the values. Emissivity is 0.2, the second plate is 0.7, and the radiation shield is 0.1 both sides. So just calculating this, we will get the flux as 806 watt per meter square. So this was the same problem with shield. So in the last one we have derived the same thing with shield, and then we derived for the same thing without shield, and then we found the ratio between with and without shield. So it was like around 1 by 6. So any doubt here? So that's it for today. I mean, we are almost done with the radiation part. So next week I will not take class on Saturday. So the last class I will take before Saturday. I have not decided when to take. So I will inform whenever I will take class. So I guess the NPTEL people will send the mail accordingly. So yeah. So next class, I guess I will be discussing questions based on in test results.
Okay, sir.
Okay.